Hello everyone, my name is Alisa Burova and I'm virtually here to present our paper which was written in collaboration with industry, with the Kone Corporation and called Utilizing Virtual Reality and Gaze Tracking to Develop Augmented Reality Solutions for Industrial Maintenance. The goal of the paper was to explore the potential of virtual reality technology coupled with gaze tracking to address prototyping of industrial AR solutions. We focus on how experts involved in the development process perceive the benefits and challenges of the approach in the industrial context. Augmented reality is known as a promising technology for industrial maintenance, and in particular it's been applied to provide in-field guidance and enhance safety awareness. However, the development of augmented reality solutions is often frozen in the proof of concept state due to risk associated with testing in hazardous industrial context. Industrial training in VR brings significant value due to the extended adaptability and the possibility to safely simulate dangerous operations and contexts. Moreover, the flexibility of virtual reality simulations make them a feasible and efficient approach to address augmented reality development issues. Within VR, potential AR concepts can be evaluated in a realistic, simulated context, and aspects like information presentation, interaction techniques, and context-sensitive functionality can be tested in a safe environment. Integrated to head-mounted display gaze tracking provides extended analysis possibilities for the usage of the augmented content and other user behavior, and it has been already applied to measure learning and safety awareness. In VR prototyping and training, gaze tracking can provide an understanding on how maintenance technicians perform their tasks, how they notice and utilize the elements of AR. To address our study goal, we developed the XR Safety Kit Framework, a multi-purpose virtual reality platform with augmented reality simulation and gaze tracking to support both augmented reality prototyping and virtual reality trainings. The system was made with the Unity game engine and the existing 3D CAD models of an elevator shaft, technical elevator components, and maintenance tools. The distinctive feature of our VR-based system is the augmented reality mode, where augmented reality field of view is simulated by displaying content over a rectangular area, 40 degrees horizontally and 27.5 degrees vertically, which is centered to the user's field of view. This mode allows evaluating of AR features, in our case in-field guidance and safety awareness, in a safe and controlled environment. It also allows the testing of different hardware aspects of augmented reality presentation, such as field of view, image quality, colors, and transparency of objects, and so on. The system allows training of remove and replace tension weight maintenance task. To provide step-by-step guidance, we created a documentation panel tool. We call it DocPanel. It visualizes instruction in the form of text, pictures, and animations over a wide square. The user can move the DocPanel in the 3D space freely and center it to eye position. The instructions are extracted from existing technical documentation in HTML format. We also designed 3 multimodal warning types to inform the user about possible hazards. The first one, the animated safety warning, uses an animated picture to explain the danger and appears over a risky area when the user interferes with it. When image is out of the user's field of view, the system visualizes a red arrow to point at the danger and makes a warning sound. Second is textual notification, which uses text and image to explain the risk. The notification is displayed over a risky object and stays for the duration for maintenance subtask. Third type uses image to notify about the danger and voice to explain it. Red arrow also appears if the image is out of the user's field of view. There is a brief demo video to visualize what is documentation panel and other system functionality. This is a feedback sound. The system assists the user by highlighting all the components related to the task. And there is animated safety warning. The The described system design is a result of iterative user study with experts. The first iteration was carried out to verify the concept and collect ideas and requirements for the system. 4 expert participants explored the designed virtual environment without defined instructions and answered interview questions, which determined our design solutions. The second iteration was focused on investigating the usability and efficiency of the in-field AR guidance and warnings in general. The outcomes of this stage resulted in the deployment of 3 types of safety warnings and advanced logging for gaze data and virtual objects. The focus of third iteration was purely on safety and evaluation of DocPanel usage with gaze data. The second and third iterations were based on performing the maintenance task in the system, and in total 9 male experts participated. 2 of them had no experience in elevator maintenance, but were specialized in information architecture related to it. The rest has at least 25 years of elevator maintenance experience, with a mean in 15. The evaluation session took place in a spacious meeting room in the premises of the company. Prior to the virtual maintenance task, the participant had a training session to get used to the environment and learn system functionality. And after completing the task, the participant filled in the questionnaire about their experience and answered the interview questions. The majority of the participants show enthusiasm toward the idea of utilizing a head-mounted AR display for in-field assistance. The main advantage was seen in easier access to information and safety awareness. With provided guidance, all the participants in both iterations successfully finished the maintenance task. The documentation tool was found to be useful for the maintenance context. The participants spent on average 35 and 4% of the session reading the instruction. Gaze data showed that participants were able to read the instructions from documentation panel without directly facing it. On average, the gaze vector angle suitable for reading was over 7 degrees. All the participants verified the need for visualizing in-field safety warnings in a real context. However, not all safety warnings were observed by the participant. The analysis of gaze data from third iteration showed that the participant's gaze was directed on animated safety warnings. Only 4 out of 20 times the warning was displayed, clearly demonstrating the failure in design. However, textual notification was found to be the most successful and was noticed 7 out of 8 times it was shown. Overall, the XR Safety Kit framework was perceived as a viable innovation for the industrial context. The participants showed eagerness about the possibilities of working with both AR and VR technologies in their daily routines, and further ideated on how such technologies could be integrated into the company's processes for testing new maintenance method and technical documentation and for risk assessing. After the iterative study, we utilized digital content from the system and created a digital survey with the goal to gather expert opinions on the usefulness of the AR within VR approach and gaze tracking in the context of industrial maintenance. The digital survey consisted of 3 parts and included textual description with videos, open-ended questions, and 29 statements answered on a 5-point Likert scale. 12 experts, 10 male and 2 female, participated in the survey. The survey results showed a positive perception of and eagerness in utilizing AR, VR, and gaze tracking technologies. The AR within VR was found to be efficient and safe approach for industrial AR prototyping, while head-mounted display integrated gaze tracking was seen as a viable analytical tool for prototyping, training, and documentation development. The XR Safety Kit framework was found to be suitable in the industrial context due to flexibility, safety, and advanced analytics. It provides a safe and resource-efficient way for AR prototyping, which may be easily deployed by utilizing existing materials in industrial context. Integrated gaze tracking brings an advantage to gathering detailed and objective data for further analysis, which could not be gathered via traditional user study methods such as interviews or questionnaires. Finally, our work shows the potential of the whole mixed reality continuum to address other industrial processes and enable collaboration between different departments. These may be further explored to support virtual collaboration, training, and documentation and method development. Thank you very much for your attention.